So hope you are fine and performing well. So this is the video lecture which I have prepared as a continuation of our discussion called Physics of Micro Nanoelectronic Devices 2. You know that physics of micro nanoelectronic devices is a very complicated subject, and if you are out of at least 2 weeks, it's very difficult to refresh our knowledge on it. So when we'll meet even after 2 weeks, that is hopefully after 14th of April, we may have a difficulties to understand these subjects clearly. So as a part of this activity, what I thought, like, to prepare a video lecture on it and share with you and see how good it is. I'm really waiting for real feedback from your side. Okay, so here I'm going to discuss called the concept of band structure. Okay, so as per our understanding that suppose you have a piece of materials or piece of any nanomaterials, and if you have a particular contact on it, what I would like to know, what is the current flow of these materials. Okay, and with these things that we have derived a formula of current, but we came across a concept called the density of states. Definitely there is another concept called the potential, that is called the equivalent potential into the materials when you apply some voltage in all the direction. That is different issue, and that's no doubt is a complicated. So one great problem that we are facing is actually called the density of states. Now how to calculate the density of states? Based on our first semester knowledge, we know that if you want to calculate the density of states, we need to have a good knowledge about the energy eigenvalues or the position of energies. If you know the position of energies and if you know the morphology of the semiconductor, you will get to know what type of or how to calculate the density of states. The most important part is that how to find out the energies values, okay, or EK diagram, energy at different k values, momentum. Now the basic the fundamental way to solve this problem, to solve Schrodinger wave equation, and that is fine. We don't have any problem on the Schrodinger wave equation. Eventually we have solved Schrodinger wave equation of one-dimensional crystal. That's not an issue. Yeah. We have written a code for it. We had a discussion on this, how to write a code on that, right? I hope you can remember. It's called the difference method. But what we have realized that for one-dimensional crystal there is no issue to write the conventional the code. Okay, but the problem starts if it is a two-dimensional. But still, if it is a two-dimensional matrix, if you have a good knowledge on spherical coordinate, you can convert the two-dimensional problem into one-dimensional problem. You can write a code on it. The problem starts if you have a three-dimensional material, and definitely it is a huge volume of the matrix. Even a supercomputer is very difficult to solve. Now the question is how to solve a three-dimensional problem. And if we can solve the three-dimensional problem, definitely we can. What we can do, we can calculate the density of states, and that density of states we can put into our current equation. And if you know how to handle the self-consistent field of potential, we can calculate the current. Okay, so kind of we realize the density of states, finding density of states problem is very critical. Now today what I am going to discuss a concept of band diagram, which is very important to find out density of state. So the important part is that we know what is called the band diagram by default, because we have started our graduation, our first semester, we know the concept of band diagram little bit. But if you just focus on this second semester lecture, so this is the first time that I am introducing a term called a band diagram. Never before I have not introduced the concept of band diagram. Okay, now this is really important. Like Now the question is, if we don't introduce the concept of the band diagram, so what is the conventional way to solve the Schrodinger wave equation and get to know about the energy values? And that is very easy, that not easy, but that is very conventional way. So if you follow my cursor, like you saw, this is actually my Schrodinger wave equations. If I R is actually vector, means if it is a spherical coordinate, how to represent those things. H dagger squared by 2m and del square u. U is the potential. This is the different potential. So don't confuse the potential inside your current equation. Okay, little bit different. So this potential is the nuclear potential. Suppose you have a hydrogen atom. Okay, so you have a 1 electron and 1 proton or 1 positive charge nucleus over here. Okay, so how, and this is the attraction force or the force between the electron and nucleus. So that is, I'm talking about the nuclear potential. Now hydrogen atom is very easy, but what's about helium atom? So if the moment helium atoms come, you are going to handle 2 more electrons. Okay, now that means U is the potential, nuclear potential, and if you have any electrons, so that is also potential due to electrons. So it is actually kind of overall potential, that U. And the conventional way to solve these things, and we have to solve it by self-consistent field theory, that we have already know how to solve this SCF. You have done a lab assignment also, so not an issue on it. But the problem is, as I told you, the moment you have a 3-dimensional, 1-dimensional, it is easy to solve, because you have a periodic crystal of, not periodic, sorry, let's not introduce called the periods at the moment. So you have like a series of hydrogen atoms, okay, but it's 1-dimensional. So you can easily calculate the energy values, by solving Schrodinger equation. The main way to how to solve the Schrodinger wave equation, you have to convert this differential equation, because it's a differential form, to matrix equation. Once you have a matrix, then you can have a difference theory to convert it to a proper code. That we have done it. But the moment you 1 dimension, it is very easy. Now what about 2-dimensional crystal? 2-dimensional crystal, to solve 2-dimensional crystal, there is a few method that we had a discussion. Kindly refer those notes. But important thing is that we have introduced called the spherical coordinate over here, and that is quite good. It nicely convert 2-dimensional problem into 1-dimensional problem. We have solved it nicely. But what's about 3-dimensional problem? It's very difficult to solve. Okay. So that means we have realized the problem of solving Schrodinger wave equation 3-dimensional system. Okay. Now the question is, kindly remember that this all theories are discovered, I think, more than 70 years back. At that time, there was no computer, no supercomputer. Now, how these geniuses have solved it? So they have solved, maybe they have solved it by analytical method, but they exactly match over the experimental method. Okay. So there must be some way to solve a problem in 3-dimensional. Okay. In this case, there are multiple methods are there. So a very good method to solve such a problem is called the basis function problem. Okay. That we already have. We have already introduced the basis part. Look at that. Just follow my cursor over there. This is my conventional Schrodinger wave equations, right? The main idea is that we need to have a energy eigenvalue, that is E, and phi r is kind of called a eigenfunction. If you somehow convert it to a matrix, okay. Now another way to solve these things, like you write this phi r, this wave function, with some basis function. Okay. So this is kind of basis function you have over here, and like I have told already that there are lot of basis function people have into, like Gaussian function. There are a lot of simulation called the Gaussian simulators. So it's telling that this UM is nothing but Gaussian. Okay, and then you try to find out the phi f. Phi m is nothing but a coefficient. It's just numbers. So if you know the numbers or this phi m, you can reconstruct your fire, and if you can reconstruct your fire, so you can reconstruct your waves. That's the idea. Okay, so but what is the good uh, function that we need to consider here to for this to solve such kind of complicated Schrodinger wave equation? I think atomistic wave basis function is nice and good, and let's take such kind of atomistic basis function. What is called the atomistic basis function, that I'll tell, but I think it's a good way to start our knowledge to consider a atomistic basis function. Then we construct, with the knowledge of our coefficient, we can construct the fire. I think it is as simple as it is. Okay. So now there are two methods that people have introduced here to solve this Schrodinger wave equation. That is actually, one is actually first principles method. I told you that Korn-Sham got Nobel Prize on it. The idea is like that: if you have a fire, if you represent fire, it's such a, like with some coefficient and basis function, and if you recalculate your equation 1, that is Schrodinger wave equation, it looks like this one. So E, energy, S, phi is equal to H, that is Hamiltonian with the wave function. Okay. Now, what is the component of S? Okay. So S component can be find out like with this method, like SNM is equal to UN dr. Okay. So NM, and what's the component of H? So that is also can be find out HNM. And how to handle that SNM and HNM, kindly go through my last lecture on it. So we had a detailed discussion on how to calculate SNM and HNM, and based on that how to construct the matrix over here. Just go through that lecture. So I hope it will clear. So this is first principle method, and no doubt it is actually better method. Okay, there are a lot of other problems are there, but if somehow you overcome those problems, whatever you are getting, that is good. What's about semi-empirical method? Semi-empirical is little bit tricky. It is like that you have formed that E S phi is equal to H phi, that is fine, no issue. After that, instead of calculating the each and every component of S and H, what you do, you will go to the available experimental result, okay, so that you can reconstruct your H matrix. It looks like that you have that E phi is equal to S inverse H phi, okay. So S inverse H, altogether I am taking it is like called the H bar. So it is kind of same expression like Schrodinger wave expression. Now we'll go to the experimental results on it, okay, and I try to reconstruct my H, try to adjust my H so that it can satisfy my expression. It is like an experimental dependent formulation, and whatever the data are available, with this availability of data will form the H matrix. And how to handle this H matrix, I'll show in a minute. So before I go to the how to form the H matrix, don't confuse about the H matrix. H is actually a Hamiltonian, okay, not hydrogen. Now here, don't confuse on it. So here actually I have written two hydrogen molecules. So sorry, two hydrogen atoms. So one hydrogen atom and second hydrogen atom. The idea is like you have one hydrogen atom, two hydrogen atoms, and when they come closer, somehow they form hydrogen molecules. Okay. And each hydrogen atom is having one wave function. And let me allow to take this wave function as my basis function. Maybe it is 1s, and let me take this is as my basis function. And that is what I am telling it is atomistic basis function. It's quite convenient to take basis function of atomistic basis function to solve such kind of complicated problem. And again I'm requesting you to go through my last lecture. So with these things, what we have done, we have formulated our H matrix. So how to formulate our H matrix? Go through that discussion. You see that there is a diagonal matrix is there that we have getting, and that is called the energy matrix. Okay, and cross diagonal, another diagonal is kind of it's called the relation matrix, relation component. What I'm trying to tell you, like it is like just like you have a like a H operator. Let me write, not to confuse with this. So you are actually working with H operator, no? So that means you have a one wave function here, another wave function here, and you are working with H operator. Okay. Now, so this first component of the H matrix is called the H11. Yeah. So if you can remember how we have written H11. So first component of my H matrix for hydrogen molecules, and how it is written. So if you just go back and see, like it looks like this one, like you have H1 wave function and same wave function is overlapping to each other. Means if you can remember, this is kind of, sorry, it is kind of, you have one wave function H1, another wave function that is actually multiplying by the same wave function. And in this case, you can understand that you have a higher magnitude. So H11 means you have a wave function and you are multiplying with the same wave function. Okay. So that's what you have H11. And if you go through our last discussion, you will get to know that you have what is called. We have calculated the component of H11 matrix. What's about the T matrix? T matrix is actually, this component is called the H12. So H12 means little bit different. So let me write H12 matrix here. So H12. What it means, like if you can remember clearly what I have mentioned over here, like you have control C, sorry, control C. You have one, so this is H, so this is the molecule 1 and this is molecule 2, so but they are actually separated, no? So when, and so it is actually 1 and 2, molecular 1 and molecule 2, okay, separated. So when they multiply, you see only this portion. So if I just try to write something, like only this portion is actually called my effective area portion. Only this portion, correct? Means if you try to multiply it, so only this portion is my effective area portion. Only this portion, because this is my multiplication portion, correct? So that means H11 is good because same wave function you are multiplying with another same wave function, that is fine. But H12, it is two wave function, but when you try to, because they are separated by some distance, when they multiply, so only this portion where actually cross over each other, that is actually multiplication product. So definitely H12 is less than H11, but still it has some contribution. Now this part, actually if you can refer my last discussion, this portion we have represented, I hope, by B or something, and here I have represented by T. It is like, okay, so this the relation between one wave function to another wave function, it is actually I have represented by T, and it is a diagonal matrix, and since it is actually, it's a Hermitian matrix, fine, but since it is a real matrix, real component, so there is no conjugation. So T and T actually both are actually real number. Okay. So if you can remember, that's fine actually. Or if you don't remember, just go through my last discussion. You will get it. Now once you have a epsilon, it's a diagonal, T is the part. Okay, so epsilon is H1 1. It means that if you have a one wave function which is multiplied by the same wave function, you will get a energy, highest energy, and T is actually H1 2. Like you have a one wave function multiplied by the second wave function. So you have to take the like called only the cross sectional equivalent part. Okay. Now what is the eigenvalues of this matrix? So you can see epsilon plus minus T, right? So epsilon plus T, this is eigenvalues 1 1, and this is eigenvalue. So it means what? Like you have a 1, you multiply by 1 of this wave function and 1 of this wave function. So overall you will get a continuous of these things, right? Okay, fine. And this one, another eigenvector values is epsilon minus T. What it means? You multiply 1 of this wave function, okay, but you multiply this one with minus 1. The moment you multiply this one with minus 1, what will happen? It will flip. Minus 1 with the red wave function, it will flip it. And once it is flip it, you will see that you will have a such kind of wave function. So that means you can regenerate your wave function with this nice matrix method. Okay. So this we had a discussion last time. Now the question is, this is good because we have a two such atoms sitting to each other. Okay, it's well and good. What happens if you have a series of, okay, so this is actually what I'm taking. Once you have epsilon plus T and epsilon minus T, like this is the wave function. So when two hydrogen atoms come close to each other from a hydrogen molecules, you find the energy will change. Okay, so change means, so epsilon T is higher value, though it depends on the magnitude of T, polarity of T. So at the moment, let's see that T is actually positive polarity at the moment. So epsilon plus T means it's a higher value, epsilon minus T is a lower value. So it is like a epsilon plus T and epsilon minus T. Just for convenience, let me write. So just to have, I don't know where you can find epsilon. I am not able to find epsilon here. So yeah, I got it. Okay. So here is epsilon plus T is here. Control C, Control V, and epsilon minus T. Again, I'm just telling you there is some significance. What is the value of T? Whether T is positive or negative, that actually depends on whether epsilon plus T is higher or epsilon minus T is higher. Okay, that will have a, I'll comment on it at the end of this class or in these tutorials. Okay, but as of now you can consider T is positive, so we'll get it. So two eigenvalues you'll get, E plus T, epsilon plus T, epsilon minus T. Okay, fine. Now we'll go to the next part. So what happened that you have a, so you understand that you have a hydrogen molecules, or how to form the hydrogen molecules, that two hydrogen atoms come close to each other. Now the question is, we have a series of hydrogen or series of such atoms are staying together. Okay, so you can see what I have written over there. 1 2 3 4 5, the series of atoms are actually in a one-dimensional fashion. Remember my problem. So my heading, band structure, basis function, and the multi-atom in 1D. Multi-atom means number of atoms are there and in one-dimensional fashion, and each one is having associated with wave function looks like this one, and this same wave function is a 1s wave function. Let me consider this 1s wave function. Okay, and this is nothing but my basis function, and you have a one-dimensional atom and we have an n number of, capital N number of atoms. Okay, now we try to solve it. The solving of this problem means we have to find out what is my Hamiltonian or H matrix over here. Okay, look at that. So this is my problem. That problem statement is the energy E phi is equal to H phi. Okay, now You know the phi is my column vector, a column matrix, okay? So phi is column matrix which I have written phi 1, phi 2, phi 3 up to phi n. N is the number of atoms, or where is my operation atoms, okay? And I think it's better to write phi capital N. It is maybe better to write. So let me, I don't know how to calculate. No, it's not happening. So I think, but you please correct it. There may be typo. This is phi capital N because we have to write. We have a n solution, no? So that means my wave vector or eigenfunction should be capital N. 2 number of hydrogen, I am getting 2 eigenvalues. 3 number of hydrogen, I should get 3 eigenvalues. N number of atoms means n number of eigenvalues, that means n number of solution. Okay. Okay. So how to read it? So E phi 1 is equal to H matrix into phi 1. So that is my read. Now we have to know how to write the H. Writing H is very easy. Just go back by previous things, like how we have written H for 2 hydrogen atoms when they come to each other. You see, my diagonal part is always like a diagonal means like you have a wave function multiplying by the same wave function. So that diagonal part is always like the highest energy level or E. Okay, correct? Just go back and check your notes. So this is my E. Now that means if you have a H11 should be E, H22 should be E, H33 should be, because you are multiplying with the same wave function, same. So multiplication with the same wave function, so definitely it would be like E only. H44, H55, H66 up to HF. There's no issue. Now what happened? So this is clear. Like now we have to write the matrix of H12. H12. Look at here very carefully. What happened to last part? We have written H12 like you have a hydrogen atoms and you have a wave function. It's like that, hydrogen atoms, and you have a wave function of atoms, and you have a actually equivalent. Only this portion is actually important. Only this portion. Okay. If you can check, this is my only this portion. I don't know, it's not clear. Maybe this one. Only this portion is important. Equivalent part is important because here actually we are multiplying. And how to write H12 we know. And this actually something called the T. We have represented it by T. No. Now you go back to the next slide. Okay, if you, so you know that all the H11, H22, H33, H44 to up to Hn we have written E. H12 we have to write by T. So let me. So we have to write T. How to write? Let us go for. Let me write T here. Sorry. So let me write T. Okay. So that means what it is telling is, it is telling that H12 would be T, fine. That means that if you go to that, so H and 1, so let me just correct it a little bit. Okay, and let me, this is fine. Let me represent it to the different color. That will help us a lot. Okay. So you see the H12 which we have represented, and this is the only portion that we need to worry. The cross-sectional part, like you have only this part. So this is actually the equivalent part, like when they cross to each other. So this is part. So that we have represent one. Like now, so here if you look at that, if you follow my cursor, like H12 it's related. Some contribution is there. So how H1 is related to H2, and what is the relation between H1 to H2, that I have represented by T. Because this matrix, this wave function are sitting to each other. Right? So 1 or 2 should be related by T. Similarly, 2 and 3 related by T. 3 and 4 related by T. 4 and 5 related by T. Why it is related to the same function? Remember, here actually one great assumption we have taken, and it's called the periodic lattice. So it means all my atoms are sitting in the periodic interval, same interval. Look. So if they are sitting in the same interval, so the distance between 1 or 2 is the same, same as the distance between 2 and 3. Similarly, same as the distance between 3 or 4. So, and since there is the same atoms, so in that case, the wave function of the same atoms are same. So they are separated by same distance because it's a periodic lattice, and the wave function are same. So that means the overlap area is kind of same, and the overlap area here actually we have represented by T. Right? So 1 or 2 represented by T, 2 and 3 represented because they are sitting each very close to each other. So similarly, H12 matrix, that is also kind of, I can write it's actually T. No issue. Okay. So similarly, if you see that H2 3, they are sitting to each other, so that also I can represent by T. Similarly, this is 3 4 T. Similarly, this is 4 5 T, and this is T. What's about here? It is actually 2 3. How they relate? 2 3 and 3 2 both are same? No. So T, 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 maybe T. Okay. Now the question is, what happened to this matrix? Just look at, that is H13. Okay, H13. Look at that. H1 is here, H3 is here. That means middle there is a 2. Okay. So what I'm trying to understand, like, what is the relation between H1 to H3? That means one atom ahead. 1 and 3. So it is actually very negligible, no? Very, very negligible, because you look at this part. One is just again change my color. Here, so 1 or 2 are very close to each other, but here 1 and 3 are very separated by 1 atom distance. So the contribution of 1 and 3, there is no such. Since they are not coming to each other, the contribution are very zero or negligible. Right? So H13 is equal to 0, 14, 0, 15. All these components you can put as 0, 0, 0, 0. Now here is the difference. So now the question is whether it is really 0 or still some contribution is there. Actually, analytically we can say it is 0, but actually it is not 0. There is still some contribution is there, but it is very, very negligible. And there is a difference between the first principle study and semi-empirical method. First principle people will also write the contribution of H13, H14, H15, all these things based on the matrix formulation, based on their this expression. Like this expression, SNM and all these things. So they will write all the contribution based on this part. But here what happened, since we are studying like analytical solutions, we can neglect this part. We can avoid this part. Telling that H1 atoms and H13 are so far away from each other, so they are not really talking to each other. Since they are not talking to each other, contribution is actually really, really low. Okay, so we can write it nicely. So you have all the component like that, and you can pull it by 0. You can fill 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 it by 0. All these things nicely. You can write on all this. You understand? The moment you go far away, so you will put another 0. Okay. Now, once you write here all this matrix, now the question is, that means you know H. E phi 1 is equal to H matrix you know, and that phi 1, that's the column matrix you know. Now, how to write that part? So let us write the matrix E phi 1. E phi 1 is equal to phi 1 epsilon plus phi n plus 1 t, right? Correct? That's what. Or like how to write this matrix. So you can write H4 E phi 4 E phi 4 is equal to epsilon phi 4 plus T phi 3 plus T phi 5, right? So that means if we try to consider a arbitrary position, suppose nth position, n is a small n position, how to write? E phi n is equal to epsilon phi n plus T phi n minus 1, previous one, plus T phi n plus 1, the next one, right? So that means since you know H, so you can write n is actually any arbitrary position. You can suppose this is my n. How to write? So epsilon phi n, okay, epsilon phi n, then you have to go previous one, T phi n minus 1, T phi n plus 1, right? So that's what we have written the whole part. Now the question is, what next? We know that matrix part. So if you know the matrix part, so this is my formula over there, we have written down. Now, what is the best solution? So you know there's a differential equations part, you know that we have to choose the solution. And how to choose the solution? So it's a 200-300 years old mathematics. People know what is the set of solution can satisfy a particular differential equation or a particular series. They put such kind of solution and see whether it satisfies or not. It's simple like that. So we have taken the solution like phi n is equal to phi 0 e to the power I n k a. Maybe possible solution if we take, and we actually put it back over this expression and try to see how it looks. So if you do all these things, you will get a solution like E is equal to epsilon plus 2t cos ka. I hope it is understood. Like you have taken a possible solution, that solution it feed it back the main expression like E into phi n e to the power I n k plus epsilon into phi n. All these things you have put over there. Then I n k it actually cancel out, so you will get ultimately this E is equal to epsilon 2t cos k. Now you know that you have a relation between energy and K. K is Ka. Okay, what is the A value? A is nothing but the distance between the atomic position, that 1 and 2 or 2 and 3 and 3 and the periodic interval or the lattice constant, whatever you can see. This is K. Now how to plot it? E versus. So this is my energy plot and this is actually K, and it's a cosine plot. So you know how to write the cosine plot. And what is the best value of cosine over here? So when K is equal to 0. So when K is equal to 0. So remember this is a Ka value. So when K is equal to 0. So you will get epsilon plus 2t. Okay. And when Ka is equal to minus pi, so you will get the lowest value. So here it is a minus pi, here it is a plus pi, E minus 2t. Okay. And it's telling that here actually E, this value is equal to E minus 2t and this value is equal to E plus 2t. Okay. Where K is equal to 0 and K is equal to pi. That means like what is the distance? What is the distance from here to here is equal to 2 pi. It is actually 2 pi distance. So from here to here, is the pi plus pi. So total distance from minus pi to plus is actually 2 pi. Okay. It is quite significant. And what does it mean? So does it means like if you are here, okay, suppose you are here, if you travel exactly the 2 pi distance, you will get the same function. Like if you are here, if you add 2 pi, whatever position, whatever may be the position, if you travel exactly the 2 pi from your initial position, you will get the same wave function. That is the beauty. For an example, suppose you are here, okay, and if you travel exactly the same, yeah, you will get it same 2 pi. So what I'm trying to say, suppose you have a 2 pi here, you would have taken arbitrary position where it is coming down. Okay, so if you travel exactly the same 2 pi position, you will get this exactly the same answer, same wave function. So if it is a coming down, so if the answer, the solution over here, and if you travel 2 pi extra, the solution over here it is same. That means nature of the wave function over here and nature of the wave function over here it is same, because it is a periodic crystal, right? So if you travel 2 pi, exactly 2 pi distance, you will get the same wave function over here and here. If you are here, if you travel same distance, you will get the same, exactly the same wave function. It is telling you like that. Now the question is the same, different. Question is that, is that Ka value, all Ka values are acceptable? Like, see, you look at that. K is actually called the angle of cos. So like, it is like it to 30, 30.1, 30.3 or 30.6 or 30.9 or 30.10. All are acceptable over here? No. So we need to find out. So what is that actually? So I think you can discuss there. We had a discussion of the periodic crystal lattice, and it is telling you something else, like the last portion. So like nth crystal lattice. So go back to my part. So nth crystal, the wave function over here, it is exactly the same the wave function over here. Because I don't know what is here is next, but what I can consider from here, it is exactly the same over here. And that is the beautiful assumption, actually helps a lot to understand the properties of any semiconductor. With this beautiful assumption, we have gone through all the way, only the last part we have assumed the last wave, nature of the wave function, it is exactly the same the first one. Only this assumption, actually there is no physical background on it. Why we have taken it? It is just like a mathematical easiness. If you take all these things, and with this assumption, whatever solution you are getting, it is actually 90% it is matching the experimental result, and we are happy on it. We should be happy on it, because 90% matching of experimental results is quite good enough. Okay, so that is, with this assumption, what we can think. So phi n is equal to phi 0 e to the power I n k a. Now this phi n is the previous one, so it should be like 1, no? Like, right? So that is also actually should be 1. Then only that phi n, if you come back to your previous one, should be 1. So to e to the power 2 I n. So it should, again, there is some typo is there. We have to be careful on that part. So how to, this should be phi 0. Okay, fine. So what we can do, we can banish it. That is helps a lot. This should not be here, huh? So because phi n is equal to phi 0 e to the power I n k, it exactly the same of 360 degree. If you travel by 360 degree, you will, because it's a periodic Parondale condition, so it looks like that you have traveled up to this one. Now this one exactly match this one, so you have to wrap it around. That is 360 degree, right? Same thing it is happening actually, and the multiplication of this 360 with some integer, that's value is there. we just refer to all our discussion with the first semester. So 2 pi n and this part, and then k is equal to 2 pi n by n. So here it tells like that. It's not that all values of k a are acceptable. Only the integer values are. So 2 pi n. So n, the small n is equal to 1 means 2 pi by n. 2 means 4 pi by n, 3 means 6 pi by n, like that. All these values are possible. Now my question is, how many solutions that we are expecting? N, capital N solution, like, correct? So like for an example, like we have 2 hydrogen atoms which forms molecules. How many eigenvalues we got? 2 eigenvalues. Suppose you have 3 hydrogen atoms. If it forms 3 hydrogen molecules, somehow, how many eigenvalues? 3 eigenvalues. So that means these are the solutions. So if you have a capital N number of atoms, so how many solutions? Capital N number of solutions. Now the question is, with this minus pi to plus pi, how many solutions are there? Can you calculate it? You can calculate, no? Because this is actually 2 pi. This is 2 pi. Okay. And what is the minimum distance of one discrete level to another discrete level? That also you can calculate. How many? 2 pi n plus 1 minus, 2 pi n small n plus 1 minus 2 pi n plus n. So if you subtract it, you will get 2 pi by n. So 2 pi divided by 2 pi by n, you will get only the n number of. So that means within minus pi to plus pi, you get all the answers. That means all the solution, which is nothing but a capital N. So you should not look the other part. You can go to other part, but if you travel even the other part, but after the interval of 2 pi, you will get the same solution. So there is no necessary to repeat the solution. So if you just concentrated between minus pi to plus pi, you will get all the solution. And that is the beauty of this assumption of periodic crystal and that periodic boundary condition. Okay. Now here actually I'm giving you one homework. Like if you go back and check the EK diagram properly, so we are actually considering the EK diagram of this lower part, not the upper part. Okay. Now why it has appeared over here? Why not it has appeared here? Because if you just go back and check that our earlier EK diagram, you say that it looks like this one only. This one only, right? EK diagram is like, but here actually you see this EK diagram appears over here. Now what is the difference? Why it has happened? This is also correct. What we have discussed, that is also correct. Now what actually matters? Okay. So that actually is your homework, and I think you should be able to answer it when we will have a discussion on it, when you come back to institute. Okay. So next part we'll have a discussion on that. What happened? Basic function and multi-atoms problem in one define. What happened? It's a 2D or 3D. Okay. That we'll have a discussion. Okay. Fine. Thank you.